Thank you. So Rebecca invited me to come here and talk to you about Cscl, computer-supported collaborative learning. And it's a complicated task to discuss this. Since Cscl necessarily combines the two cultures of computer science, computer technology on one hand, and interpersonal collaboration on the other. And you can see from the lengthy title here that I gave my talk that it's a complicated business with several diverse facets to it. So methodologically, I consider case studies. That's how I approach research in Cscl. So I thought I would present a Cscl case study today, describing a particular Cscl project at a specific point in its development, namely the VMT project that Rebecca summarized in her introduction, and where we are in the VMT project at this point, this week, this year. So the project is, as Rebecca mentioned, a collaboration between the iSchool at Drexel and the Math Forum, as well as with Rutgers. Arthur Powell is a co-PI from Rutgers Newark, where he's the collaborating PI from there. Cindy is on our advisory board of the project. So it's a collaboration with people from also the Drexel School of Education. And so it includes people from diverse disciplines, as Cscl necessarily does. So I'd like to start at the beginning, back a couple thousand years ago, because we're dealing with geometry and we're dealing with cognition. And literate cognition started back then, largely with Euclid's Euclidean geometry. Back in the classical age of Greece, from about 500 to 300 BC, around 500 BC, geometry was developed by people about whom we know very little other than their theorems. And around 300 BC, Euclid codified it in his book, The Elements, which has been used ever since as the main textbook in geometry until very recently. Most literate people around the world read that very book. In our project, we're now undertaking the modest task of translating Euclid's Elements into something for the 21st and 22nd century. We think it's time for an update. So here we see in the picture, which is not a photograph, but somebody's imaginative drawing, of Euclid on a clay tablet. Kind of looks like an iPad, but it's a predecessor of the iPad. Using two tools basically, other than the pen or scribe, a straight edge and a compass. And these are basically the tools that we still use in geometry, although you'll see digital versions of them. Euclid may have studied in Plato's academy. So if you think of the influence of both Plato and Euclid on Western society, it could scarcely be stronger. They basically, the two of them, defined rational Western thought. And that's important for our project in Cscl, as you'll see by the end of my talk. So jumping ahead to the titanium age of our society, of computer-based society, here we have basically the same construction, but no longer on a clay tablet, now on a computer. It has some digital tools here, some of which are the equivalent of straight edge and compass. And we've done the same construction, basically exactly the same as Euclid did. which was his proposition number 1 in his first book of the elements. There are some differences, however, that make this dynamic geometry rather than Euclid static geometry. So one is we have some color here, so we can highlight specific things. In Euclid, everything looked the same, so it was hard to tell what was significant or salient to a proof and so on. We can also grab, with our cursor, we can grab a point here and drag it. Although I can't do it on this screen, I can do it on my computer screen, and then see the triangle. It's really different. In Euclid, it would be a different triangle. It's a different drawing. Here it's continuous. This one drawing is dynamic and can be changed. And you see that it's still a right angle here. So the construction has made a triangle with the right angle. And no matter how you change the triangle, as long as you don't destroy the constraints that were built in, you see it retains that. In the GeoGebra is a computer application that allows you to do these things. You can also see different representations. So here you see a list of the symbols and some of their characteristics, like their coordinates on a grid, their lengths and values of the angles and so on. And you can see that no matter how you drag it, this angle alpha in here stays 90 degrees. So it not only looks like it's a right angle, but its measure is 90 degrees. You may note as a curiosity that it's still called angle alpha, just like Euclid called it. So we use Euclid's language, Greek, to label things still. So a lot of things haven't changed, and some things have changed very significantly. And I want to talk a little about the significance of this transition or translation from Euclidean geometry into dynamic geometry. The other aspect of our project is discourse. In addition to the dynamic geometry drawings, we focus on the discourse of students talking. One particular theory of discourse that's popular in education these days is called accountable talk, and this is an idealized chat log of what accountable talk might look like with a software agent. So here we have a chat room with 3 students and a software agent engaged in discourse about the drawing that they've done in Geogebra. And one student says something mathematical about the drawing, and the software agent pipes in with this accountable talk prompt to the other students to make their understanding of what's going on accountable to each other, and to be accountable for the understanding of the other students, because this is we want this to be a collaborative setting where the students are collaborating, and part of collaboration means that you make, as one participant, you make sure the other participants are following what's going on. And so the agent prompts and asks Chris, can you check that Max is following what Sam said? And they kind of do that, because this is an idealized chat, not a real one. We'll see an example of a real one, and it's a little bit different. And so we've developed in our project this is the VMT with Geogebra application. So it has a tab here of Geogebra where we've embedded the Geogebra software, and it has a typical chat over here. And so it combines the drawing with the discourse in an integrated way so that the students can talk about their drawing as they're doing it. And then they can also see different representations of what's going on mathematically. And they can discuss that. And they can even, the chat has some features which I'll describe later, where you can point from the chat into the drawing and so on. So This VMT project, the Virtual Math Teams project, has been going on, as Rebecca said, since about 2002. And we've been developing the system gradually using design-based research approach, and we're still doing that. What we've introduced recently is Embedding Geogebra, which is an open source dynamic geometry application, but it's only been developed in the past for single users, and we're interested in collaborative learning. And so by embedding it in here with the chat, we've converted it to a multi-user system, which has been part of our technical development. And this is really the first multi-user dynamic geometry system in the world. So we've taken what is a leading single-user system and made it multi-user. What multi-user means is that if you have several people in the chat room, they all have access to this drawing simultaneously. They can all manipulate it, add to it, and see what each other is doing, as well as discuss it in the chat. So they work together collaboratively on the drawing, which is something that probably took place in Plato's Academy when a number of students gathered around the clay tablet and worked collaboratively there. But actually in the development of geometry in Greece, geometers were scattered at different city-states of Greece, and so a lot of the work was done asynchronously. A lot of the development of geometry originally was done asynchronously through written discourse. And so we will also want to support asynchronous collaboration, and I'll talk about how we do some of that later. So our goal in the project is to provide a technological medium and an integrated pedagogical approach to collaborative learning of mathematics. And we're interested in translating Euclid's static individualistic presentation of geometry into a form that takes advantage of the potentials of computer support and computer power, as well as collaborative learning. So we're moving from clay tablets to computers while preserving the unifying principles of geometry. And we're especially concerned with the nature of the discourse that takes place around the mathematics. So this is central to both collaborative interaction and to cognitive understanding. And so one of the main things we're doing is we're concerned with the pedagogy. So we're developing curriculum now that emphasizes student-centered exploration, noticing, wondering, and manipulation, visualization, representation by students, rather than memorization of authoritative content. So our current specific tools and our work is focused on developing a document to serve as a curriculum for both teachers of mathematics and students. So we're quite literally translating Euclid's book of constructions and proofs into a scripted set of activities for dynamic constructions and collaborative reflections by small groups of online students. So Cscl has existed as a research field for almost 20 years now, but it still remains more a promise than a set of results or than a classroom reality. But this is not so surprising if you consider the complexity and the vision of Cscl. And this complexity is just becoming clearer as the field develops. A lot of what we're learning in the field of Cscl is how much more there is to figure out. If you think about the development of literacy, back in ancient Greece and so on, when writing and drawing became systematized, and back in the Renaissance when it became available to the majority of people. It's really taken hundreds, if not thousands of years for literacy to spread and be adopted. And it's a tremendous transformation, social transformation, from an oral society to a literate society. And it may be somewhat like that in the transition from a literate society to a computer-based society, one where everybody feels natural doing dynamic geometry and doing collaborative chat and so on. So it's a non-trivial task to try to introduce these things into normal classrooms around the world. So today I'm going to go over these 8 topics related to the VMT Cscl project. So because Cscl is a vision rather than a widespread practice, we're not able to conduct large randomized clinical trials to prove effectiveness and efficiency. At best, we can show case studies of what seems to be possible. Point 2, we need to be expert in the field of geometry education. You have to understand the text well in order to be able to translate it. Point 3, we recognize the central role of discourse. Discourse is always complexly situated in its context, and so it's hard to study and to generalize, but we have to do that. Point 4, to explore promise, we have to gradually prototype new technologies. It's not like schools are already using these technologies and we just have to go in and do big studies of many students. We have to develop the technology first and introduce it into classrooms and then study it. Point 5, for a complex technology like GeoGebra or VMT with GeoGebra, the technical issues are really subsidiary to how the students actually use the technology in concrete situations. Point 6 is the research cycle in which technology and pedagogy and collaboration co-evolve, raises a large number of design issues, and I'll discuss some of the design issues that we're facing right now. Point 7, for the analysis of what the users are actually doing in case studies and the nature of their discourse, we rely heavily on microanalytic methods that we adapt from conversation analysis. And finally, with its broad vision, Cscl raises a number of philosophic issues, and I'll end my talk by bringing up a couple of what I consider the philosophic issues. So we're trying to develop a set of activities that can guide students to develop an understanding of the essential relationships of geometry. Tools like GeoGebra provide many ways to highlight and display focal objects. They allow students to observe and actually take control of the step-by-step construction rather than just seeing the resultant diagram. Color, coordinates, values of lengths and angles, etc. can aid their visualizations. And students can manipulate constructions, drag objects, and observe the consequences. Students can explore variations in the construction and see what difference it makes. They can explore how objects behave given the dependencies on other objects that they've built into it, the construction. Multiple representations show that a given fact can be seen and established in different ways through lengths, coordinates, relationships, etc. For instance, a concrete generic triangle can be dragged to look like any triangle situated anywhere. The collaborative setting and the guiding curriculum encourage math talk and articulation of what students see, notice, and wonder about. So in education theory today, it's popular to think, a popular theory is situated learning. And this views learning as a matter of becoming socialized into a discourse community, such as the math discourse community. And so we look at, that's how we look at the learning that we want to promote as a socialization into the math discourse community. In particular, collaborative learning can be defined this way. So being a good citizen of the math culture involves accountability to other members of your group, the community in general, and to the field and principles of mathematics at the level of high school math. It's also well established that the best way to learn a subject is to talk about it with others, and that's a basic principle of collaborative learning. In fact, deep understanding of math, which is a tricky concept, can be defined and operationalized as the ability to talk about a math topic in multiple ways. For instance, in terms of geometric constructions, algebraic equations, spreadsheet columns, graph curves, drawings, physical models, etc. And the Geogebra software provides multiple representations, and our curriculum encourages multiple ways of talking about geometric relationships. So in our project, we focus on what we call significant mathematical discourse as the primary empirical indicator of collaborative and individual learning. Among the forms of discourse we will be looking for are forms of accountable talk related to math content. Here we have a response structure involving a software agent that you saw before that facilitates accountable talk moves among a group of 3 students. Each student's postings are shown in a different column, and they're connected by who's responding to whom. So this is a representation of a conversation analysis view of the chat log that I showed earlier. So while some research in Cscl is done following a traditional experimental design with a controlled variable, control group, randomized subjects, and quantitative measures, most Cscl research follows more of a design-based research approach. This is partially because it involves the design of new technologies. So it is a design process. The Cscl technologies change the whole learning and task paradigm, so it's not possible to compare with the control group because the task itself has changed. You can't hold that constant. Also, research in classrooms is so highly situated that conditions are not reproducible, which is a basis for traditional experimental. But at an even deeper level, so much is just unknown that it's not possible to hold everything constant. We don't know all those things. We don't really have a clear theory of what goes on in collaborative learning. We don't have a fixed technology, and so on. So all those facets have to be explored simultaneously: theory, technology, pedagogy, analysis method, etc. So we begin at some point and allow everything to develop and co-evolve through evolution, as clearly indicated. Everything is connected to everything else and changes continuously as the project evolves. One of the gears is the project team, which meets together weekly around this table and projects data up on the wall and discusses it collaboratively. So collaborative learning is not just something that the students do, but it's something that the teachers will be doing as we train them in their professional development. And it's something that the research team does. We collaboratively learn. And that's what gives us a feeling that our analyses are not idiosyncratic. They don't follow the bias of one person, but they have the decisions that we come up with in analyzing the data are the result of different perspectives from people who are experts in math education, in psychology, in education, in computer science, in information science, in psychology, and so in anthropology, and so on. Most importantly, PhD students, because they're the ones with the fresh perspectives. So I'm going to go through some of the aspects of the computer support, even though that's not necessarily the most important part. It is a central part of the project. We're trying to develop an integrated socio-technical environment for cognition at different levels, and we have various components of the technology to do that, and we try to integrate them as much as possible. So this is a screenshot of what we call the lobby. This is the first place a student comes in order to browse through different topics and find activities and chat rooms that they want to participate in. The lobby also supports some social awareness features, not quite as complete as Facebook. We don't try to compete with them. And you can also, for instance, a teacher can view what's going on in a particular chat room here and produce a log and other outputs to analyze what's taking place in the interactions. From the lobby, you typically go to a chat room. As you seen before, it could be have a tab with Geogebra displayed there and a chat. But there are many possible tabs that a chat room can have. It can have a shared whiteboard that doesn't do geometry, but for posting notes and simple drawings that's shared by the group. And these, for instance, are also GeoGebra tabs, but for individual students to work in. So an individual student can explore geometry in their own space, which others can see if they want to, but typically don't. And then also a shared tab that the whole group works in. So it's supporting asynchronous or private individual work, as well as synchronous group work. We can also have a display of the topic and a wiki page. So typically, when a group has finished their work, they might summarize their work in a summary tab, and then copy it to a wiki where it can be shared by other groups who have maybe done the same project, and then different groups in the classroom or across classes can compare what they came up with. So these are some of the main features: the summary whiteboard, the wiki pages, logs. We can generate spreadsheet logs, and we have a replayer, which I'll show you. Right now, our main focus is on developing the curriculum that will be used by students in this. And also, next year we'll begin professional development and training of geometry and math teachers, so that they're familiar with and comfortable with using this environment and can use it in their classrooms with their students. This is a wiki page which would be shared by a class or a number of classes. This is one we used a couple years ago, not for geometry, but for probability theory, where we had a number of different probability problems for students to work on, and a number of different typical strategies that they could use for solving probability problems. And we seeded this with, for one of the problems, we had examples of how to solve that problem using each of the different methods. And then the idea was a small group of students would pick a problem and a method that they wanted to use, would work on that, and then they would summarize their results, and it would be stored in one of these cells here, and other groups could go and see and compare. So this is just a way of consolidating what a number of groups did, so all the groups can see what each other did. And the wiki provides a nice systematic way of doing that. Here's the replayer. This is really important for researchers, and we hope it will become important for teachers as part of their professional development. Essentially what it does is it shows exactly the VMT environment, the way the students saw it, with at the bottom this extra little sort of VCR interface where you can set it to replay through the whole session at normal speed that the students used, or double speed, or 5 times the speed. And you can also scroll this bar through the history, so you can bring it to any point, and it synchronizes the drawings with the chat, so you can see what was going on at that minute. Typically, a researcher would focus on a couple-minute segment as a case study, an excerpt, and would very carefully go through action by action, go through and see how it unfolded. And this is invaluable for research. And the idea with teachers is that they could look at, replay a session that their students interacted in, and identify crucial learning experiences that took place, or problems that arose that they would want to go back and deal with. But it provides, it captures a complete picture of what went on in the interaction. So here are some of the major issues that we face today. That's why I'm glad Loretta and Arthur are here, because maybe they'll think of some solutions back there while I'm talking. So at least they may have other ideas of what the hot issues are, but for me, thinking about this, I listed 7 issues that I think we're dealing with in the project. One is how to balance instruction versus exploration. And none of these are really, or most of these are really not yes-no questions. They're typical design trade-off issues. How do you balance things? How do you balance instruction versus exploration? And we tried, a progressive approach to pure exploration. Just throw some problem at the students. Let them sink or swim. Some of them sang. But very few of them did what we had hoped they would do. Some did interesting things, but we really want, so we have a limited time, in a class, in any course, you have a limited time to get across certain basic ideas that you want. And in order to do that, you have to provide some guidance. But we don't want to just lecture the students, and we don't want to just tell them, look, this is what we want you to see. Do you see it? Write it down, we'll check it, you got it, or you didn't. We want to guide their exploration and give them the necessary background instruction that they need in order to do effective exploration. We want them to notice things on their own. But of course, as teachers, we want them to notice the things we want them to notice. So it takes some guidance, and that's a tricky thing. And so we're writing the curriculum, and every week we sit down and we try it out as a group, collaboratively, and then we reflect on how it went and how we should change it, and we go back through many, many drafts. So that's an iterative, design-based research approach. Synchronous versus asynchronous learning. That's the basic distinction in computer systems and in online learning. Are you teaching a group of students who are meeting together at the same time, even though they're might be spread around the world geographically, they're meeting at the same time and chatting with each other collaboratively, which is much more productive than asynchronous, where you might have to wait 2 days to get a response to what you said, and by then you don't care so much about it. And it takes forever to reach complicated decisions. But asynchronous has a lot of advantages. In mathematics, people are used to trying to think of a solution to a problem by going into a quiet, private place and really focusing without the distractions of interacting with other people. But we want them to work collaboratively. So how do we balance those things? So that's why we have the private Geogebra space for them to work by themselves and try things, and then a space where they can work together and discuss it collaboratively. Then Geogebra, as I said, was developed as a standalone for individual users. So it has some really nice features that we'd like to incorporate. So as a user of Geogebra, you can create your own perspective, which means things like you create your own toolbar. You pick the tools that you want to use all the time, and you make them easily available to you. So for instance, you might want to, so Geogebra comes with a very complicated toolbar with literally 100 different tools to pick from. So it's hard, takes a little bit to find what you want. Suppose you want, as a teacher, you want your students to only use the tools that are equivalent to the straight edge and compass of traditional Euclidean constructions. So you want a toolbar with just 5 tools on it, maybe. So you want to define that and make that available to people. So you can, in Geogebra, make a custom perspective like that. But because Geogebra was a single user system, that's fine. If I make a custom perspective, it's available to me on my computer. It doesn't hurt anybody else in the world. Other people don't see it. I don't see their custom perspectives. But what about in a collaborative system? If I'm a teacher, I want all my students to be able to use my custom perspective. But I don't want students who are not my students to be bothered. I don't want my students to see the custom perspectives of 1,000 other teachers around the world, because they would never find mine. So how do we work that? The same thing for custom tools. Geogebra has this extremely powerful and important ability to make custom tools. So if I do that construction you saw for a right triangle, I can make a tool that, with the click of a button, produces a whole right triangle without going through the 6 steps that it takes to do a construction for it. So I do the construction once, and I save it as a custom tool. Now suppose I want my class of 30 students to each create their own right angle tool. Well, then it has to be available to each student individually, but not to the other students. Suppose I want to create one as a teacher and have my 30 students use it, then it has to be available just to my students. None of that is worked out for Geogebra. So first we have to decide, how do we want it to work? And in different scenarios, we would want different things, so how do we deal with that? And then we, of course, have to program it, so it works the way we want it to. But at this point, these are still design issues. Although it might be interesting to have our programmer develop some so we can try them out and see how they work. That's the design-based research approach. And then the agents, like this agent for accountable talk. We'll see that just because you have a software agent saying things, it's not always helpful. It can be totally destructive of the whole collaborative process. Cindy's smiling because she already saw the results of one of my studies of it, where it was a total disaster. And does it have to be a total disaster? Hopefully not. And what?
You'll figure it out.
We already have.
Yeah,
partially.
I'm waiting till you do.
I know. Because it's a design-based research cycle we have to go through. We find out it was a disaster the way it was done the first time. So what do we have to change that would make it better? As I said, the curriculum is going through constant weekly redrafts. And our research agenda, so to get the latest grant, we had to spell out, a year and a half ago, we had to spell out how we were going to do our research. Well, our research changes every week. Our agenda changes every week. Every week I ask Arthur, what should we do next week? So it's a little different than NSF expects when they say, for a 5-year project, 2 years before you start, you have to spell out exactly how everything's going to go and what your results are going to be. If it's research, you don't know what the results are. That's why you're doing the research. So I'm going to go through each of these a little quickly. So exploration versus instruction. Here we had an activity where we give the students 4 triangles, and they look pretty much the same, and we ask them to explore it. So you explore it, you grab a corner, vertex point, and you drag it somewhere, and you see what happens. In some cases, it changes the shape of the triangle. In other cases, you just can't move it. You can move the whole triangle, but you can't pull any point on it. And in each of the 4 cases, they act differently. The triangles act differently. And what we want the students to see is that we've constructed these triangles, we've hidden the construction, but we've constructed them with certain dependencies or constraints. So one of these is constrained to always be an equilateral triangle. So you can make it bigger or smaller, you can move it from here to there, but you can never pull one corner to change it so that one length is not the same as the other lengths, or one angle is not the same as the other angles. One is constrained to be a right angle triangle. So this angle is always going to be 90 degrees, and you just can't pull anything, any part of it, in a way that will use that 90-degree angle. You can make the whole thing bigger or smaller, you can make these angles different, and so on. One's an isosceles triangle, so 2 of the sides are constrained to be the same size. And one is just a generic triangle, so you can do anything you want. And so by exploring this, so at the beginning of their use of dynamic geometry, they see that geometric objects, despite appearances, may have some hidden constraints based on how they were constructed. And then in future activities, they'll learn to do those constructions. So the next question is, how would you construct a triangle so that it's constrained to have 2 sides equal? How would you construct it to be an equilateral? How would you construct it to have a right angle? And those are the future activities that would come after this. So I already talked about the fact that we have these personal spaces. So first they can explore, and what we did was we put this set of 4 triangles in each of their personal spaces so they could explore that individually, say before class or before they collaborated. And then it was also in their collaborative space. And so then, having explored it in their private space, then they could discuss it. They could say, one person could say, I think that the red triangle is constrained to be an equilateral triangle. And another could say, oh, I hadn't really seen that, but I had trouble trying to pull it or something. So they can talk about that, and they can talk about, for instance, one question was, can you move the red triangle to lie exactly on top of any of the other triangles? Well, if this is an equilateral and this is a right triangle, then it's going to be impossible to make this triangle, no matter how you make it smaller or bigger, and no matter how you change this, they'll never be able to lie exactly on top of each other, which is a visual way of saying they'll never be congruent. Whereas these two can be congruent, this one can be congruent with anything. And so one of the tasks is to make a chart which triangles can be congruent to each other. And that leads their discussion. That's supposed to encourage their discussion of how the different ones are constrained. This is the custom perspective tool. So here you have, if you choose the menu for perspectives, you have a number of predefined perspectives, like your basic geometry or your more advanced geometry. But you can also have custom perspectives, like here's one I created that's equivalent to compass and straight edge tools. And there's an interface for managing and saving them and so on. And then, like I said, the question is, who gets to see what list of custom perspectives? And how is that shared in a multi-user environment? And the same with the creating a new custom tool. So here I'm trying to create a tool. I've constructed this triangle, and I say, create a new tool whose input objects are any 2 points, A and B, and whose output objects are the 3 sides of a right triangle, where it's constrained that the angle at point A is going to be a right angle. And so I save this, and then it appears on my toolbar. If I select that tool and click 2 points on the tab for point A and point B, up pops the 3 sides of a right triangle. Very nice, but who gets to use that tool? We don't know. I'll get to use it with my students. So here's the agent, the software agent. That we're exploring how can this work. So how much, it's also kind of a trade-off of instruction versus exploration. Should the agent, how instructional should the agent be? How leading should the agent be? Should the agent be authoritative and say, and order Chris to check that Max is following Sam? Or should it be a helping agent that if Max says, agent help me, I don't understand what Sam is doing, then the agent comes in and says, Chris, can you help Max? So that's a matter of designing a design issue for the software agents. And as I said, the biggest thing we're working on now is the education curriculum, how to guide the development of skills and tacit understanding, which we want to get across. So it's very much a developmental process we want the students to go through. And Euclid already understood that. If you read his book, it starts with certain basic axioms and definitions, and then it builds up a series of theorems that build on each other. You can't do theorem 4 if you haven't done theorem 1 and 2 yet, because theorem 4 uses the results if they're in one, and builds on it, and builds on the definitions and understanding that you had before. And that applies to really all aspects of learning geometry and learning collaboration. They're developmental processes, and you have to start at the beginning and have students build on it. And not knowing, different students come into it at different levels, so you have to deal with that and make sure that they all have the basics that you need. So that's a very tricky criteria. In fact, I wrote up 5 or 6 pages of design criteria for the curriculum, how you develop proof, knowledge of proofs, for instance. You can think of proofs. So traditionally, a proof is the kind of thing that Euclid did in his book. But a more sophisticated view of proof is that there are different stages of doing proofs. So younger children think about things. They may not lay out a formal proof the way that Euclid did, but they have sort of at their level the equivalent understanding of why something works the way it does. And you can develop that, and there's analyses of 4 or 5 levels that lead up to formal proof. And so we want to lead students through that developmental process. And then design-based research. So how are we going to conduct our research? As a team, doing tests, working with teachers, working in classrooms in future years, and putting together the technology and the curriculum that we need to do what we've promised to do. And how do we know that we're doing well on it? And so evaluation is an important feature, of course, in research. And as I said, we build on the idea of conversation analysis. So conversation analysis is an approach to the study of communication. People in this school probably know about it. It was developed in the 60s by Harvey Sachs and his colleagues, and adopts the approach to social science of ethnomethodology. It was developed by Harold Garfinkel around the same time. They took advantage of tape recorder technology, which had become available in the 60s. We take advantage of computer logs in our replayer in much the same way. They worked with informal face-to-face conversation. We're working with online mathematics discourse, quite different, but involves a similar approach and a similar kind of analysis. And we've spent time trying to translate from one to the other. So our theoretical view is that at the center of individual learning and cognition, small group learning and cognition, community learning and cognition, the center of that is sequential small group interaction. So the kind of interactions that we see happening in the chat room among a small group, their discourse, obviously it's fueled by their individual understanding. Obviously it's the centerpiece of their small group work, and it also feeds into and is influenced by things at the community level, whether you consider the community the classroom that the group might be part of, or the larger school math community. And there's also the tasks that we define for them that feed into the interaction, and they come up with their group knowledge artifacts, which is what we want to see them develop, and that's their response to the task and their outcomes. And so we analyze this and this to see how they're, not only how they're doing it, but how they're doing it. So it's important to us not just to measure, you know, is our approach going to yield higher test scores? Yes or no, by how many points? But we want to understand how they're doing what they're doing. And that, to me, you know, Rebecca held up my book on group cognition, so this is where group cognition happens, and this is where we evaluate how it's happening, what's going on there. And we can do that in considerable detail because we have these computer logs that are replayable. And we can make representations like this. So this is the data that, this is real data from using a software agent in a real classroom, not one of our geometry classrooms. This was a biology classroom. And in the first column, you see the posts of the agent, and in the other three, the three students' posts. And just visually, from sitting back there, you can see that the agent was dominating here. And the students were responding occasionally to the agent, but that's not collaboration. They weren't collaborating with each other. Later, once the agent became quieter, the students ignored the agent. And that's when they started to respond to each other. And here you see what looks like, visually looks like, could be a very interesting collaboration between two students, and here it runs to be three students. So at this point, they're collaborating maybe nicely. You'd have to look at the content to see, are they talking about biology or are they talking about skateboarding? But at least visually, they're talking to each other, not just to an agent. I mean, our goal isn't to have them talk to an agent. Our goal is to have them collaborate about the content. And so my conclusion from this is that we failed to have quite a while before they could even start collaborating.
So here you're equating the kind of the responses or the communication as an indicator
Right.
for the strength of the collaboration.
Right.
Right? But that communication is a part of collaboration,
Right.
but it doesn't necessarily mean collaboration. It could be, as you say, they could be just talking about random stuff, has nothing to do with the task.
Right.
Or even if they're talking about the task, may not really be sort of, I don't know, considered as real collaboration. So if you study that, and actually I'm curious about the other arrows. I mean, all those blue arrows are basically just responses.
Right.
So what are those green and red arrows?
So the red was mediation of accountable talk. So here is something like probably the agent says to one of them to ask the other to do something. And so here you see this one responding to this one, responding to this one as a result of this, possibly. The green is content uptake. So here there's some content, but as you're indicating, there's no, this representation is not showing a real content uptake here.
Because to me, that's actually, the green one is more interesting, because then that's really kind of contribution or sharing kind of happening. And it's possible that it's happening through those messages, those responses, but one then needs to do the content analysis to see, because often we find in collaboration, one of the common actions is, hey, look at this is what I found, kind of thing. And it may be hidden somewhere in that message where they're just communicating. But that's kind of a stronger indication of collaboration than simply saying a message, which could be anything.
Yes, and we do, conversation analysis looks more closely at the content of the words actually said than any other method. It looks at pauses and their significance. It looks at implications of this word choice versus some other word they could have used to say the same thing. And that's why it's called microanalysis. It's extremely detailed. It's much more detailed than, well, than this, for instance, which just looks at the response structure, which is an important thing to do in chat. Or than coding, if you just coded each of these into 3 or 4 categories, that's not a very detailed look either. You would say, you know, some are off topic and some are about biology. But how much does that tell you? Are they saying the same thing about biology? Are they disagreeing? So it depends on your coding scheme. But conversation analysis looks at the individual words used. And so you're right, this is definitely not the whole picture. What I tried to do here was just get a quick view. And actually for our design-based research process, this was the important thing, to see that the agent was interfering, was dominating at the beginning, that the students eventually ignored all that agent was saying here, and that it took them a long time to even start responding, regardless of what they were saying. Just to be responding, that's sort of a precondition. You can't have a deep collaborative discussion if you're not responding to each other. So this was enough to say, back to the drawing boards with the software agent. It's too invasive. It's too dominant. And that's all we needed to know in order to redesign it for the next time.
And
Now, I do, in my next slide,
sorry, go ahead.
I do look further, and so here's an example from mathematics. This is a recent paper that I did at the last Cscl conference. And I did a more detailed analysis of the response structure of students working in VMT at the end of a 4-hour-long sessions. So most conversation analysis, in fact, almost all conversation analysis that's published in the field looks at very short responses. It'll look basically at 2 people and how one person is responding to another. That may take a couple turns, but it's basically one response that they're looking at. But I wanted to look at longer sequences. I wanted to see how a group can solve a math problem, which is more than one response. And so I analyzed the response sequence of this particular interaction that took a couple minutes. As I say, at the end of, these people had been collaborating, had been chatting for 4 hours about various problems. They had come up with a problem that they were interested in, and they were having a lot of trouble. This problem took them an hour at least. They were getting confused and so on. But here towards the end, there was this long sequence, long bite, conversation analysis game. And I looked at the response structure, and I broke down this excerpt into 10 conversation analysis sort of elements. So a typical conversation analysis would have looked at just one of these and would have found something interesting about how the interaction took place there. But they wouldn't have looked at the whole sequence. So I looked at the whole sequence, and when I sort of labeled what was going on in each of these 10 responses to each other, I found something that I thought was really interesting. Namely, isn't this the way most people solve math problems? If I solve a math problem, well, I look at the topic, I decide, well, this is interesting, let me think about this. How am I going to approach it? I identify a pattern that's going on, maybe in the data, in the mathematics, and I try to figure out an equation. And then I try to decide, is this a good equation to solve the problem? And I may check some special cases and confirm, yeah, this is a good solution. And so then I formalize it, I write down the equation, I say this is the answer. And then I figure I'm finished. So this is a typical sequence that an individual solving a math problem would go through. And this is the sequence that this group went through, as a group. And I looked, and it's not that one person is saying, okay, let's start, let's pick this approach, and the other people or person is just responding. They take turns initiating, another one responding. But as a group, they go through this typical pattern. And they were extremely excited when they solved the problem, because this had been bothering them. It's a problem they picked themselves, and it had been bothering them for a long time. And they were getting frustrated, but they stuck with it in the VMT system and solved it. So this is the kind of thing that we want to see more of with GeoGebra. We want to see how some of the steps in here use the dynamic geometry tool to draw some conclusions. And we want to be able to do this kind of microanalysis of the discourse to identify exactly what they've accomplished. So on that high note of students actually solving a problem, not getting distracted by our software agents and so on, I want to conclude with some of my own philosophic reflections. Taking a step back to our 2,000-year long perspective of what we're trying to do. So how can our dynamic math system enhance geometric cognition by individuals, small groups, and communities? These are all important. We're not, at least I'm not just interested in individual learning. I'm not just interested that the students who participate in this get higher test scores and go on to Algebra 2. I want to see how the small groups that they're in solve these problems, just like the last slide showed, the small groups solve the problem. How do they do that? And how does the community learn? I mean, if you think of Euclid's predecessors, we don't even know the names of the people who really invented geometry. Euclid basically pulled together the theorems that were floating around Greece at the time. But other people, we don't know them as individuals. We don't know the small groups of the little local schools that they worked in when they worked out these original theorems. But we do know the results of the community of classic Greek geometers. And that result, their cognitive accomplishment changed the world radically. We wouldn't have computers now. We wouldn't have modern science. We wouldn't have mathematics if not for their community. So can the VMT community do something like that? Presumably. Okay. But there's some things we need to worry about. So we want to integrate. If you look at our technology, we have this GeoGebra, and we have the chat. We have the rational planning of geometry with its dependencies, software functions, scripts, curriculum, software agents, all of that rational, highly rational stuff on the one hand. And in the chat, we have the normative social practices of collaborative learning, accountable talk, human motivation, and distorted communication. And we want to get a synthesis of those two. And so if you look at a face-to-face small group working, you can sort of see it going on. You know, on the screen they have some rational problem that they're dealing with. They're trying to figure out, in this case, you know, which rocket is going to go the highest. So that's a rational calculation based on dependencies and so on that they're trying to understand. But you can see in the, just from their bodies that they're negotiating how to understand what's on that screen. This person's pointing something out to the other people. And that's what we want to happen in our chats online. So geometry is really the paradigm, has always been in the Western the paradigm of what you could call purposive rational calculation. And you can compare the structure of a classic proof. You state the conjecture to be proven, you construct the deduction, and then you restate QED, that which was to be proven. And we get that structure from Euclid's book. Every theorem has this structure in his book, and we've adopted it. And that's the general form of planning. We set a goal, we implement it, and then we reflect on our accomplishment, making sure that we've completed the goal. And it's the same paradigm in computer programming. We develop the requirements, we do the programming, and then we do the testing. So this approach to rational thought has permeated our society. And dynamic geometry makes this visual for students. They can see the constraints being applied. They apply them themselves, hands-on, the constraints to the construction, and they build it up themselves. In Euclid, you saw the finished diagram, but you did, and you were stepped through it somewhat, but you didn't really build it yourself. Here, they're building themselves, at least in our approach to the activities. We want them to do that. We want them to understand how they're building these dependencies into the construction. And that's why the proof works, because they built it that way. It's not that this is some ideal figure, came out of the sky, and it just is that way, and the proof works because it's wonderful mathematics. No, it works because you built that construction to be that way. And you understand, if you understand what you've done, you understand already the proof. So our hope is that group geometric cognition that we're developing can integrate the purposive rational thinking and the social normative action. So Jürgen Habermas is one of the great contemporary philosophers in Germany. He talks about, in fact, the central point of his whole life's work is the duality between the logic of efficient work and the logic of social interaction. His contribution to philosophy was to make this distinction, number one, and to say, number two, that we need to integrate them. We need both. We can't throw away rational thought, but we can't just go by rational thought. The focus on rational thought, actually, for him as a German growing up post-war, he saw that as part of what led to fascism. Fascism was rational in a way, in a very antisocial way. It ignored the logic of social interaction. And the response to that kind of consequence is to have a synthesis of these, to integrate them. And so we're trying to do that in a very narrow domain of learning geometry. But the proper balance of these is a precondition of democracy. And I think that's something that my heroes would all agree on. Certainly that was central to John Dewey's theory of education for democracy. So while classical geometry epitomized the literate worldview, dominated by factual propositions and fixed truths, and that was, so, Plato, he had this idea of fixed ideas, fixed forms. There was a whole world of these fixed forms, essences. That's just the way things were. It's not like in the real world, he distinguished. The real world, things are always changing. know, this bottle used to be full, now it's half full, and maybe in a little while it'll be empty. In the ideal world, things don't change. There's the concept of bottle. The concept of bottle is not going to change just because I drink from it. And the same with geometry. Those were eternal essences. They never changed. But dynamic geometry can be used to show people a different view of things. That, like I said, that this construction is true not because of some eternal essence, but because you constructed it that way. And you can understand that. You can make the dependencies visible. And so truths are seen to be socially constructed, understandable and modifiable. And don't forget that, you know, people often assume that a lot of truths in this world are socially constructed, but not math. They always point out, if you're a social constructivist and somebody wants to argue with you, the first thing they'll say is, what about math? What about truth in math? That's eternal. That's not socially constructed. But I think here we see that in a sense it is, by constructing these dependencies. And so, in conclusion, while Euclidean geometry did point the way for rational thinking in literate Western society, and therefore was a tremendous positive thing, and culminated in computer science and artificial intelligence, what could be better? A Cscl approach to dynamic geometry that we're trying to develop can integrate that kind of rational thinking with interpersonal understanding, and can show the socially constructed and negotiable nature of rationality. But accomplishing that in classrooms around the world is a non-trivial task that we've begun, and maybe some of you will continue it beyond what we're able to do. So that was what I wanted to share with you.